Okay, so we got the power rule. Okay, I need you to stop talking, please. We lost time at the beginning because of the technology, so I can't fight that. All right, so power rule, n x to the n minus 1. This is our constant function rule. If it's a constant, the rate of change is 0. Constant multiple is that if you have a constant multiple times a function, the rate of change is that constant times the rate of change of the function. And then the sum or difference of functions, sum or difference rule, is just like we would hope it to be. If you have a bunch of functions added together and you want the rate of change of that sum, you just take the rate of change, the sum of the rate of changes, or difference, okay? Or difference. So here's what we have so far. So we're going to do square root. So if we wanted to do the square root function, we want to prove what its closed form is. How do we start? How do we start proving a closed form or deriving any closed form? Right, we start with our difference quotient. We know that it's going to be f of x plus h minus f of x all over h. And so in this case, that is radical x plus h minus radical x over h. So what do we do with this? So we go back to algebra 2, and we remember this is our difference of squares rule, that a minus b times a plus b is a squared minus b squared. This is going to be very helpful in this derivation. So how are we going to use that? Well, we've got the square root of one thing minus the square root of another. So that looks like a minus b. It'd sure be nice to have a squared minus b squared. Those square roots would go away, right? We squared both of those. So how are we going to get from a minus b to a squared minus b squared? It's telling you right there. Multiply by a plus b, which would be these square roots, but added together. Okay, so that's what we'll do. We'll multiply top and bottom by square root of x plus h plus square root of x. And so we're doing that because the numerator is going to turn out nice. We're going to get a squared minus b squared, and the square roots are going to go away because squaring a square root, those are inverse functions, right? And so that makes the square root go away. So our numerator becomes x plus h minus x. There's the a squared minus b squared. And the denominator, just that thing multiplied. And so then the numerator just becomes h, and like all the other examples we've done, we've got the h in the numerator, h in the denominator. They can go away. And so when h becomes small enough, we get 1 over 2 square root of x. Okay, so for time's sake, if you want to write that down, I'm going to refer you to the video later on, okay? So, this is what we found. 1 over 2 square root of x. But you'll notice, what is square root of x? It's x to the 1/2. So we could check we've proved it, or we've gone through a derivation, but we can check that derivation using what? We can use the power rule, okay? So we can check our result using the power rule. And the power rule says that it'll be 1/2 x to the 1/2 minus 1. 1/2 minus 1 is negative 1/2. Well, x to the minus 1/2 is 1 over x to the 1/2, which is 1 over 2 square root of x. And so, check. We got it. This is just a check of what we did before. Okay, so we just added another rule to our list, okay? Square root of x is pretty common, so 1 over 2 square root of x. Or if you're just holding on to a exponent, 1/2 x to the minus 1/2. Okay, so exponential functions. So here's a general form of an exponential function, some base to the x. Okay? So is it xb to the x minus 1. Can I do that? Why not? So thousands upon thousands of calculus students in the past have done this. Why is it not right? Because we're thinking about the power rule here, right? So if we had x to the n, we know that its rate of change is n x to the n minus 1. So what's in the power rule, or so in that x to the n, what's the input into the function? What's the input into the function? X, the base, right? The base is the input, and n is some constant, right? X cubed, x to the negative 5, x to the 100. What's the input into this? The exponent is the input. All right. So here in our power rule, it's where your base of the term, x to the n, is the input. Here it's where the exponent is the input. Totally different animal. Okay. Totally different function when your input is the exponent versus your input being the base. So it's definitely not going to follow the power rule. It's going to be something else. Something else. How do we find out what this something else is? Write the first step. Go. Everyone write the first step. We're going to try to figure out what is the rate of change of b to the x. How would you start? How would you start? Okay, what do we think? How are we going to start? No, but where did that come from? Okay, Jasmine. B to the x plus h minus b to the x, she says, with all over h. Is it right? This is it. This is our rate of change of b to the x. So it would be what? F of x plus h minus f of x all over h. Okay, what can we do with that? So what's b to the x plus h? B to the x times b to the h. And then we notice we can factor out b to the x. And we're left with b to the h minus 1. I'm going to do both steps here. Inevitably, you will ask about this. So we get b to the x times this ratio. And if we want exact rate of change, what do we do from here? Let h get really, really small, right? And so that it's indistinguishable from what you would get if h was 0. All right, so h is really, really small, so that this is indistinguishable from what it would be if h was 0. So if h were 0, what's the numerator? 1 minus 1. So this is, or as h gets very, very small, that ratio goes to 0 over 0. What's that? No, so it's b to the h is 1, but it's 1 minus 1. Okay, so as h gets very, very small, that approaches 1. The numerator approaches 0, the denominator approaches 0. So we're heading towards 0 over 0. So what do we do with this? Is that 0? Is it 1? What this is called, this is called an indeterminate form. There's 3 possibilities. Three possibilities for 0 over 0, depending on the context, okay? Possibility number 1. 0 over 0 could be 0. Okay, so as h gets very, very small, in certain contexts, 0 over 0 would approach 0. In certain contexts, it approaches a constant, a non-zero constant. And then in certain situations, 0 over 0 gets really, really large without bound. Okay, it gets large without bound. Or the smaller you make h, the closer you get to 0, just the larger and larger it gets. Okay, so we have the rate of change of b to the x is, look, what is that? What is b to the x? It's our original accumulation function times this. So let's talk through these possibilities. Could this be 0? Doesn't make sense because we know that the rate of change of an exponential function is not going to be 0. The rate of change of a constant function is 0. So it doesn't make sense that that would head towards 0 because we would be saying that the rate of change of b to the x would be 0. Well, that's not right. Okay. Let's skip to number 3. How about this thing going to infinity? What do we think of that? So if the rate of change approached and infinitely just got large without bound, that would mean that for any x value, a small change in x would result in an infinite change in y for every value of x. Is that going to be right for the rate of change of b to the x? No. Nay. So all that's left is that thing, this ratio, heads towards some non-zero constant k. So what are we saying? We're saying the rate of change of b to the x is some constant times the original function b to the x. So the rate of change is this is gonna head towards some non-zero constant, but it's gonna be, that rate of change function will be that constant times the original function we started with. This is certainly seems like that could be the case, whereas we know it couldn't be 0, we know it can't head to infinity. So we want to figure out what is this constant then? What is the constant? So here I'm showing 7.5 to the x. This is the graph of 7.5 to the x. And we're going to kind of explore this idea that, so what's our conjecture? We're saying that f of x is 7.5 to the x. Our conjecture is what? What do we think is true? That the rate of change of f? Yeah, so our conjecture is that the rate of change is k times 7.5 to the x. That's our conjecture. Okay, how can we, not knowing what the closed form is, how can we graph the rate of change of f? How could we could graph it even though we don't know what the closed form is yet? What could we do? What's that? Yeah, so let's set up the open form. Here we go. I did it up here. So I got my f function is b to the x, and then I've got the open form rate f of x plus h minus f of x over h. And we'll graph that. And you see I'm choosing h to be very small here. Choosing a very small h. Okay, so I'm going to graph that in red. Red for rate. Red for rate. So how are we going to test our conjecture here? I've got the original 7.5 to the x, and I've got its rate function. And we think that maybe that rate function is a constant multiple times the original function. So we want to check this out. So if I come over here, so here, can you see that? Is that showing up?
Yeah.
The vertical line?
Yes.
So say here is x equals 0.32. Okay, so right now I'm showing x equals 0.32, and I have the output for the original function in blue, the accumulation function, and the rate function in red. So I can find those outputs. Maybe 1.90555. So f of 0.32 is 1.9055 or 56, and RF of 0.32 is 3.84 essentially. Why am I getting this? So I got the output of the rate, and I got the output of the original accumulation function. How do those numbers relate to k? How do those numbers relate to k? What would k be if our conjecture is right? Where's the 2 coming from? Yeah, it looks like what? It looks like the rate is something like 2 times as much as the function, right? So about 1.9 and about 3.8. What is f of 0? F of 0 is 1. So what do we think maybe for the rate at 0? Let's see if it's like 2. So f of 0 is 1. The rate at 0 is 2.015. Okay, so it's looking like when the function is 7.5 to the x, this constant multiple is something like 2. How can I test that? So how would I know that that's actually staying constant for sure at 2? What would I need to do?
Choose more functions.
Choose more x values, right? And so for every x value I choose, that rate has to be that same constant, about 2 times as great as the output of the function, the original function. So what I've done here is I've set up a ratio here, R over F at the capital X up there that I've chosen. So if I change the capital X value, which is representing any x, what should happen to that ratio of R over F?
Stay constant.
It should stay constant, so watch. It's not even moving, it's not even twitching, right? So it's not even moving at all. It's just staying constant. So this is really very strongly supporting our conjecture that the rate of change function is a constant multiple of the original function. And in this case, for 7.5 to the x, that constant is 2. So let's do 4 to the x. So if I do 4 to the x, I'll change b to be 4. Is it still a constant of 2? So here is f of x equals 4 to the x in blue. And then the red one is our rate. If I change x, does the ratio change? Here we go, ready? Doesn't move a muscle, okay? So that ratio is just fixed. So write down the rate of change function for 4 to the x. Write it down. Write down the rate of change function for 4 to the x. The rate is always what?
Yeah.
1.3864 times 4 to the x. Doesn't make sense. No matter what x I pick, that red, the y value for the rate function is always 1.3864 something, 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 times as great as the output of the original function. So what about 1.6? So 1.6 to the x. I'll change this. So let's do 1.6 to the x. Write the function, write the rate of change function. The rate function is always what? 0.470015 times. So this one's, how is this one different than the first two examples we did? In the first two, our constant multiple made the rate function bigger, right? It was that constant multiple was bigger than 1. But now when I chose 1.6, the constant multiple was less than 1, and so the rate is some fraction. I mean, it's 0.47 of the output of the original function. So that kind of leads us to ask an important question. So what happens here? So here's 1.6. If I change it back to, look what happens if I change it back to 4. At 4, our rate of change is a constant greater than 1, so the rate of change is greater. At 1.6, that constant is a fraction of 1, so our rate of change is a fraction, that same fraction of all the output of the original function. So this is begging a question. What's the question? Yeah, where is that constant equal to? What the constant would, yeah, right, but we're the constant equal to 1. So somewhere around here, for some b values, for some base, looks like around 2.7, that constant is 1, meaning that the rate of change function compares how to the original function? The same function. The rate of change is the same as the original function. Okay? The value of it. So the units are still rate of change units versus accumulation units, but those numerical values of the rate of change are the same as the output. So let's get more precise than 2.7. I'll change the slider from 2.6 to 2.8, and let's see if we can hone in on it a little bit more. So where is it? So what are we looking at? Looking at this ratio right here, trying to make this ratio equal to 1. That's a lot of 9s. Okay? So maybe with the amount of precision I have here, this is as close as we can get. So somewhere around 2.718, the rate of change function actually is 1 times the original function, or it's equal to the original function. Okay? So this is a very special number, and so the exact value of this number is called the natural base. The natural base is this constant, or this base, such that its rate of change function gives all the same values as outputs of the original function. And if we want to get more precise than this, this is called a natural base. And it's E. What's up? I say 2.71828184590. What do you guys think I do in my spare time? So what's the point? It's a very specific number, okay? It's a very specific number. It's a lot like, it's the same type of number as pi, right? An infinite non-repeating decimal. It just keeps going on and on. But it is a precise value, okay? It just requires an infinite number of decimal places to be precise. What's that? Yeah. Do you doubt me? All right. So this constant depends on the base. So we changed the constant in b to the x. Change b, you have a different constant that makes your rate of change function that constant times the original. Okay, but this base called e is this very special base such that the rate of change function equals the original function. So let's go back and summarize that. So we said that, I hate that stuff. That was someone else did that. Okay. So what did we say? This is our conjecture that the rate of change was k times the original function, and we saw that was true. And so k times, and so we didn't show where this comes from, but that k value is coming later. Okay. So the k value is the natural log of b. So that's a b, not a 6. So the natural log of the base ends up being that constant value that you multiply the original function by to get the rate of change. Here's this e. That's the e that gives a k equal to 1. That's the e that gives a k equal to 1. And so here's where the rate of the original function is that function. It's the only function like it. Okay, it's the only function where its rate is the same as the outputs of the accumulation. Okay, here's how we say it as derivative, right? So we still say the rate of change of e to the x is e to the x. But this is now exact in derivative notation. Okay, so here we go. We got the 4 from before, and now we got 3 new ones. Square root of x. What's the rate of change of square root of x? Out of order. It is 1 over 2 square root of x. And then b to the x is natural log of b. That's that constant that times the accumulation function gives the rate of change function. And then for e to the x, that constant is 1. That constant is 1. So your rate of change is the accumulation function. Any questions on these rules? We'll do a practice problem. This would be good to write down. I'll give you a moment to write these down if you want. Or you should have the other 4 from before. Just the 3 new ones. If you haven't written down the 3 new ones, write down the 3 new ones. Okay, here we go. So here's one that uses all the rules we've learned so far. So let's give it a shot. But as we do it, we want to cite every rule that we use. So we come to this first. So as a whole, what rule are we applying to the whole thing kind of first? What rule applies first? Sum and difference. We have the sum and difference of functions. So each one of those, we're going to find the derivative of each one and take the sum and differences of those derivatives. That's what the sum rule says. Okay, so we come to the first one. What rule applies to the first one? I hear most people saying constant multiplication. We've got 4 times a function. So the derivative or the rate of change will be 4 times the rate of change of that. Okay? So whatever that is, rate of change is going to be 4 times that rate of change. Okay, 8 to the x. Rate of change. We just learned it. So exponential functions, we know are a constant times the original function, right? What's the constant? Natural log of the base that you started with. Okay? So I showed, in the rule I showed it before, so usually you write it after. Okay? X to the minus 8. What rule do we use? Power rule. It'll be? Okay, so negative 8. X to the... So the question is it negative 7 or negative 9? You literally subtract. You literally subtract 1. Negative 9. Okay? Plus derivative of x. Okay, so you can apply the power rule, or you can just think, oh, x is a linear function. It has what kind of rate of change? Constant rate of change. What's the constant rate of change of the function x? 1, right? So it's like m. It's like your coefficient is your constant rate of change. So 1. Or you can use the power rule. 1 times x to the 0. X to the 0 is 1, so you just get 1. Okay? What rule do we apply to minus 2e to the x? Constant multiple. It's going to be minus 2 times the derivative of e to the x. That's the one case where your derivative, your rate of change is the same as the function. We just showed that. Okay, x to the 10.7. So, I know many of you have done these before. So if you've never done these before, and I lose you, you have to ask, because I'm hearing 60% of the crowd just getting this right. So if you've never done this before, and I'm assuming that you're getting it and you're not, please ask, okay? So x to the 10 plus 7 would be which rule? Power rule, which would be 10.7 x to the 9.7. Subtract 1. Minus, we just showed that rule. Radical x is 1 over 2 radical x. Last one. Is it e squared? Okay, this is something that students miss a lot. Listen, in its nature, what is e squared? It's a constant. That's a number. That's not a function like e to the x. This is a constant or a number. So what's the rate of change of constant? 0. There it is. Okay. I will post homework this afternoon. Okay, homework will be posted this afternoon.